and estimate, like kind of like New Keynesian models, DSG New Keynesian models. So I hope it will, you will find it like interesting for what you do. Okay, so let's see if I can. Yeah. Okay. So when we're doing monetary policy analysis and designing models to study monetary policy, we sticky prices is really like a key ingredient in the model, because we want models in which money is not neutral, because we want to study monetary policy, and the kind of typical way to move away money neutrality is to have sticky prices. But something which is, I guess, known, but let me repeat it, is that by itself, the fact that prices are sticky is not imposing a lot of restrictions on equilibrium allocations, right? Because for the very reason that money matters once prices are sticky, what pins down allocation properties is really like the bundle of sticky prices on the one side and monetary policy on the other side. So it's really, if you want to know what a model is producing, it's not enough to know that prices are sticky. You also need to know what monetary policy is. And so let me give you an example with like the most simple model one can imagine that has some sticky prices, which is like the famous three equation New Keynesian model. So that's I'm gonna start with this model. So I'm assuming that everyone is more or less on board with this model. So this model has typically three equations. The first one is like the Euler equation of some of the households in the economy. Y is output, or the difference between output and what output would be in a fixed price world, and that's the real interest rate. IT is the nominal interest rate that is controlled by the policymaker, the central bank, and pi t is inflation. So there are three variables: output, inflation, and the nominal interest rate. And here there's like the demand shock, something that makes agents consuming more today given expectations and given the real interest rate. Second equation is that the typical New Keynesian Phillips curve. The idea being that prices being sticky. When I decide of my markup over marginal cost, I know that I may not be able to reset my price in the future. So instead of charging a markup over current marginal cost, I'm charging a markup over some expected average discounted marginal cost. And hence, this equation. If you solve that equation forward, you would have that inflation is like discounted sum of future markups, and markups here are, to a log linear approximation, proportional to the output gap. And that shock is, any shock that increases inflation given expectations and given the level of output. So those are like the two, equations that describe the private sector behavior. And then, the third equation that is needed to solve this model is a some policy rule. And what we do typically in in the literature is to have like a Taylor rule, which is like a relation that maps some observables, typically inflation and output, and those observables are mapped into a policy decision, which is the nominal interest rate. And so here I'm using like two possible Taylor rules that both satisfy like the narrative of what's a Taylor rule. So the first one is like the Taylor rule that which makes basically the central bank increasing the nominal interest rate if inflation is high, and increasing the nominal interest rate if the output gap is also high. Okay. Then the second one is some kind of other incarnation of the same idea. So now I'm going to increase the interest rate, not if inflation is high, but if expected inflation is high. And when you think of what central banks are doing, it's not clear whether they target current inflation or some kind of like medium run inflation that could be this expected inflation. And then here I'm assuming that what is also the central bank reacts not to current output gap, but to the growth rate of the output gap. So the idea here is that those two rules, I mean, they are different, so they're going to give like different results. But the idea, I guess, is that they're like very similar, so it shouldn't really matter whereas I use one or the other. So what I'm going to show is that for a particular set of shocks, I can get like very different results with those two rules, meaning that the model is not only those two equations, but allocations properties really crucially depend on those two questions plus what the central bank is doing. So I forgot to say that here, I just like, put some values to those different parameters. So here there's a 1, here there's also a 1 on the elasticity of, demand with respect to the interest rate. And here I put like a 0.99 and here a 0.1, which are, some values that are reasonable. It's not like very important what they are, they're just reasonable. And I'm doing like a very specific shock, just for the sake of the argument. And that shock is that something happens, which is like a shock 2 to demand and a shock 1 to the market shock at the same time. Okay, so I'm just looking at what is going on in that economy when I have this shock, and those two shocks have persistence of 0.9. So first, I'm going to look at like the measure of what the central bank is doing, and those two rules are very similar, so I should find like very similar things. And indeed, this is what I get. So here you see the response of the policy variable, the nominal interest rate, to this particular shock, which is again twice standard deviation of demand shock plus 1 standard deviation of the markup shock. And the black line is my kind of like regular Taylor rule, and the gray line is this kind of like slightly different type of Taylor rule. But again, I mean, I'm happy if you disagree, we can talk about that. But my point here is that those two rules, they share the same narrative. They describe more or less the same thing that the central bank is doing. And indeed, we see that the response of the main interest rate is more or less the same. I mean, of course, it's not exactly the same, but there's an increase in interest rate, which is persistent. One may think that what is really important is the real interest rate that is implemented through that rule. So we can look at the response of the real interest rate according to those two models, the one with the regular Taylor rule and the other Taylor rule. And again, you see like basically more or less the same thing. So it seems that, yeah, I mean, the policy is more or less the same, with those two rules. So now let us look at the response of, the other interesting variables in the model, which are inflation and output. So that's the response of inflation. And again, so we see some differences, of course, so inflation is responding much more, with this alternative Taylor rule, but it's, again, qualitatively and almost quantitatively, it's pretty similar. Good. Now let us look at the response of the output gap. And here we see that, oh, wow, there's a very, very different response. For the same shock and for what people would point like the same model, in one case, output is going down persistently, and in the other case, output is going up persistently. Of course, it's not the same model because one of the three important equations is not the same. That's the Taylor rule. So now if I put together, both inflation and output response, you see that not only output is going up in one case and down in the other case, but the co-movements are different. Okay, with one of those Taylor rules, we have like positive co-movements between output and inflation. So if you are looking at those responses, you would think, oh, what hit the economy is mainly a demand shock. But according to the other rule, you would think, oh, what is hitting the economy is mainly a supply shock because inflation and output are going in opposite direction. So that is, so this is, this very kind of like simple example is to show that, yeah, I mean, what is important is really like the bundle of what the private sector is doing, including sticky prices, and what the central bank is doing, meaning like the policy rule. Okay, so then when you think of what we do, I mean, and I include myself in the group, what we do when we design like DSG models, I mean, we put a lot of efforts in the macro foundations of everything that the private sector is doing, but we don't put we virtually put no effort in thinking how we should specify the monetary policy rule, and the idea is that it's a bit as if it should not matter, right? So I mean, my previous example is showing that, oh, well, it matters a lot. So then the question is, is that good practice? And are we doing something wrong, or are we led to, misleading conclusions if we don't pay attention to the way we model monetary policy? So, one argument for, assuming a Taylor rule is that, oh, that's, the Taylor rule is meant to describe, realistically the precise constraint that monetary authorities are facing. And so I'm assuming a Taylor rule because, I discuss with people in committees for monetary policies, with central bankers, etc. And I know that this is exactly what they do. But I mean, it's clearly not the reason why we're using a Taylor rule. We're not using a Taylor rule because it's describing the actual precise implementation of monetary policy. We're using it because I guess because people have used it before. So I'm sorry. So the two questions we're really asking in that paper is that, okay, does it hurt once we estimate the model, and once we look at the data through the lens of the model, does it hurt to assume that the Fed or any central bank is following some sort of Taylor rule? And we will show that yes, it hurts. I mean, it's bad. It can give very bad results. And second, if it hurts, and it does, is there an alternative? Is there a way to be agnostic about what the central bank is doing in estimating a model? And we'll say yes. I mean, there's a way to solve that problem. And most of the paper will be devoted to showing you what's the problem, showing you that the problem matters in practice, and then showing you how we can circumvent that problem. So what we do, two things. So exploring the consequences of assuming possibly wrongly that monetary authorities follow a Taylor rule when estimating new Keynesian models. And two, showing that there's a way to specify monetary policy that will be a linear minimal state monetary policy rule that will basically map the state of the economy into equilibrium allocations. And that rule is basically agnostic about what the central bank is doing in practice. So it's encompassing Taylor rules. And we will see that in practice, it's giving pretty different results. So what I will do, okay, so that's what we do. So two things. Of course, there's a whole literature on optimal monetary policy. That's not our concern here. We're not taking a stand of what the central bank, whether the central bank is optimizing or not. We're just trying to uncover what the central bank is doing. And once we have uncovered it, once we have estimated, in an unbiased way, all the deep parameters, then we can ask, what would be the optimal policy in that model? But that's not a question we're asking here. Okay, it's purely positive economics. An important remark in what we will do. So we will follow the practice that we will restrict models and parameters to those producing determinate equilibrium. Okay, so that's some people don't do that. I mean, there are very few people who haven't done that in the past. So we're just following the practice. So what it means is that when we estimate, one of the identifying restriction in estimation is that the economy is determinate. Okay, I can come back to that if you have any questions, but that's what we do. So what I will do in the talk. So first, I will use an abstract approach and explain exactly the kind of biases that we can have if we formulate monetary policy in a Taylor rule way. And then I will show how does it matter in a simple three-equation model that I will estimate, and then I will show that how it matters also in bigger models. So are there any clarifying question at this stage? Happy to pause if needs be.
Sorry, this is Gustavo from the bank. I have a question because at the end this is kind of like a problem of misspecification of the model, right? Something like that. Basically, you're assuming something about the structure that is not right. Mm-hmm. But I guess that Taylor rules in general are just like some sort of construct to approximate the way central bankers decide things, but they can also be seen as something like a certain guide to formulate policy and evaluate results. So essentially, basically when you have these two different, maybe the mistake that we do is just pushing too much the interpretation of what we obtain from a Taylor rule rather than, just assuming that the Taylor rule is actually the reality by which policymakers decide things, right? I don't know if you follow. It's kind of like a question in the comment at the end. Sorry.
No. It's going to be exactly this. It's what I will say is that assuming a Taylor rule we will basically put constraints on what the model can produce, and those constraints can be rejected by the data, and therefore can lead to biases in a lot of things. And so what I will propose is a way to be agnostic about what monetary policy does. If monetary policy is following a Taylor rule, I will uncover a Taylor rule. That's not a problem. But if it does not, then the estimation will be different. So it's about misspecification, but you will see that there's a bit subtlety. There are like two types of biases, and one is a bit more subtle than plain misspecification. And what I wish, and then you will see. But that's so the idea is that even if there are good reasons to believe that the central bank is exactly following the Taylor rules, maybe not the best idea to impose it in the estimation stage. And on top of that, it's clear. I mean, I think it's clear that we don't assume a Taylor rule because it's a truthful representation of what central banks actually do. And the best way to be convinced of that is to look at the wealth of different specifications for the Taylor rule in different models. And it seems that it's more about, I don't know, having a good fit in some dimensions rather than, describing accurately what the central bank is doing.
Okay,
so,
Frank, thank you.
Yes.
This is Ernesto from the bank. Very quick, maybe if it comes later, please defer the question. Bayesian methods don't bypass this issue?
Sorry, say it again.
Bayesian methods to estimate the SGEs don't bypass this issue?
No, because there's still, once you have formulated one particular formulation of the Taylor rule, I mean, you're Bayesian on the values of the parameters, but you're not Bayesian if you wish, on the form of the mapping from the state of the economy to the instrument. That's going to be it. You'll see that.
Okay, thanks.
Okay, so let me start with I will spend some time with this abstract approach. So that it's not a model which is it's not an economic model. It's just like some Y and Z's. But I think we can see a lot and understand what's going on in this abstract approach. So this is why I'm following it. So what I will do, I want to show that there are like two types of biases that one can be confronted with when using a Taylor rule. One which is like the misspecification bias. It's a bit obvious. If the central bank is not doing that, and I assume that it does, then I'm going to bias things. It's not like rocket science, but it happens that it has a big bite in practice in big models. And then there's another bias which is a bit different, which I will call a deterministic bias, which is linked to the fact that because I'm assuming a Taylor rule, I have to restrict all the estimated parameters to get determinacy, and I may do that in a wrong way if you wish. I'll show you that. So that bias is a bit different, and that's a bias that you will typically find when estimating smaller models. Why? Because small models are like very much forward-looking, so they are very prone to determinacy. So by small models, let's say the three-equation model we saw before, and by big model I mean like Smith-Wouters. And if you do Smith-Wouters, you don't get this determinacy bias, but you will have like this misspecification bias being very important. And I'll show that, and it changes quite a lot the way we, for example, we account for the fluctuations of inflation. Okay, so I'm going to start with the determinacy bias. So let me use this like simple abstract model. It's just like one behavioral equation and an exogenous variable. So that's so I have my variable of interest y, which I assume to be forward-looking. Okay, so it depends on the future value of y. Alpha is assumed to be between 0 and 1. And then it also depends on this instrument I. So obviously, you can think of I as being the nominal interest rate, but here it's like it's an abstract model. So, and then it depends on a shock, ST, which here is the only state of the economy, and that's this shock is autoregressive of order 1 with variance of 1 for the innovation. Okay, so let us think of this policy variable as something that helps controlling y. So here I'm not looking at any optimization problem in the y do I, adjust I in a particular way? I'm just assuming some policy rule. Okay, and I'm going to like assume like two different types of rules. So one will be a feedback rule. So I will make my instrument a function phi, I mean like a linear function of the, my variable of interest with the parameter phi. So so this phi is for feedback, and that's exactly what the Taylor rule. Okay, it's a feedback rule that maps some endogenous variables into the instrument. And then let me contrast this rule with what I call a state rule that maps the state of the economy into the instrument. So here, because the model is fully forward-looking, the state of the economy is only the exogenous variable S. Okay, so I have like this model with those two different policies. And my question is, okay, does it make a difference to assume one or the other? Are there some allocations that can be produced with one and not with the other? Does it matter? And in a way, you could say, so one way to think about it is to say, once I have solved that model, of course, y will be a function only of the state. Okay, that's the solution. So then, you can replace this y by some psi times s. So, so it should be more or less, it should be the same, right? So I'm going to show that it's not, there's not an equivalence between those two types of rules. So to do that, I need to basically solve the model under my feedback rule, solve the model under my state rule, and then compare the allocations. Okay, so that's easy to do, but let us do that together. And it's it's easier to do in that model than in the new Keynesian model because dimension is 1 here, so it's going to be really pen and paper. Okay, so let me start. Let me assume that the solution that the policymaker is following this Taylor rule, feedback rule. Okay, and let me solve the model. So how do I do that? Well, I'm sorry if I'm a bit pedestrian here, but let's do it. So I just replaced my instrument by the rule. Then I can put the weighty on that side, solve forward. I know the process of ST, so I know that the expectation in period t of st plus j is simply rho at the power j times st. And solving forward, I find that that's the formula that I obtain solving forward. I'm just it's infinite sums forward. So for the model to be determinate and to have a unique solution, I need this sum to converge, right? So there's a condition for that, and I would like this sum to converge for any value of the persistence parameter rho. So let me assume rho is 1, and so a sufficient condition for convergence is that alpha over 1 minus beta phi is less than 1 in modulus, in absolute value. Okay, so that's the condition. So that's the condition. So so you see that's a restriction actually, given the deep parameters alpha and beta. That's a restriction on policy. Policy cannot be anything. Okay, so the phi has to be such that this is between 0 and 1. I mean minus 1 and 1. Sorry. So to put it differently, the restriction on policy that is put by the requirement for determinacy, that would be the Taylor principle in the new Keynesian model. Okay, so it is whatever phi should not be too small. Okay, it should not be in that interval. There's no particular interpretation of it, but it's just like a restriction on policies. And under that restriction, then I can solve this guy forward by it's an infinite sum that converges, and then I can get my solution. So in the end, my solution is that the endogenous variable is a function of the state, and of course that parameter depends on the policy parameter phi. Okay, so yeah, so that's I guess so that's what we do when we solve with the Taylor rule. So now let me do the same thing with a state rule. Okay, so a rule that maps the state of the economy into the instrument. It's also easy to do. So again, I'm taking my model, which is this forward-looking equation, and then I'm replacing the instrument by this policy. The instrument is a function of the state. I solve forward exactly in the same way, and I get this equation. So you see that there's a difference between as compared to previously. So you see that here, to have a determinate solution, I need alpha times rho to to be smaller than 1 in modulus, and that doesn't depend on the policy parameter. Okay, the policy parameter because it's not a feedback rule. It doesn't impact the condition for determinacy. So under my assumption that rho is always between 0 and 1, and alpha is also between 0 and 1, this is always converging. Okay, so here that sum converges for any policy choice sigma. Okay, and the solution is once you so forward this, the solution is it's another super simple equation which tells me that there's a mapping from the solution is a mapping from the state to my variable of interest y, and it's this particular formula. Okay. So to recap, I have like two. It's this, it's the same world as far as private sector is concerned, and then it's two different policies: feedback rule or state rule, and depending on those policies, I have those two solutions. And then my question is, okay, so does it matter to assume that the rule is feedback or state? Or to put it differently, can I always obtain those allocations if I assume a state rule? And can I always obtain those allocations if I assume feedback rule? Is there equivalence between the two? Is it just a different way of telling the same story? Okay, so this is what I'm going to do now. I'm going to assume, say, that the world is feedback, and then I will look at the conditions on my state rule to replicate those allocations, and then I will do the converse. Okay, and then I will go to estimation in this simple world and show you where things can go wrong. Okay, so first, let me assume that the world, the data generating process, is a feedback rule. So the world is so that's what the world, what I observe is this, right? And then I'm wondering, can I think of a state rule that will produce the same allocations? Okay, that's my question. So a necessary condition which will also be sufficient, and again, it's not rocket science. If I want the two allocations to be the same, I need those two blue terms to be equal, right? Because if they are equal, then the path of y will be the same in the two worlds. So you see that I need this blue term to be equal to this blue term. I know the value of phi, so I can solve this in sigma, and I can find what I call my equivalent sigma. So this is telling me a state rule with parameter sigma e of that value will generate the same allocations. Okay. Good. So here we can see that any feedback rule allocations can be replicated with a state rule allocation. Okay. So in a way here, if I'm assuming a state rule wrongly, it doesn't matter, because it doesn't matter because the thing that I will not know what the central bank is doing in practice in its implementation. If you think that this is the implementation, meaning that the central bank should look at y and decide of I so that I is phi of y. I just know that the central bank is in the end mapping the state into this I, but the allocations will be the same. Okay. So now let me do the converse. Let me assume that the DGP is the state rule and see if I can replicate it with my feedback rule. Okay. So that's what I do here. So stop me if it's unclear here, because I'm playing around with what's the DGP and what's the rule. But yeah, so please stop me. So you remember we computed already those solutions, and so now again, so I'm wondering whether there is an equivalent phi that I call phi e, such that if I follow a feedback rule, I can replicate the solution of the model with the state rule. Okay. So again, I will need those two guys to be equal, the blue guys. Okay, that's the condition if I want to replicate the same allocations. So that's fine. So I can I just need to solve this equation in phi, and I can find like basically there's an equivalent phi. So meaning that there is a feedback rule that can replicate the same allocation as the state rule, and that's the value of phi. But here I am, I need to check that I have determinacy with that phi. Because you remember, when I do a feedback rule, I don't always have determinacy. It depends on the value of phi. So the question is, But this phi e, does it belong to the proper interval so that I have determinacy? Meaning it has to be outside this interval. But you see that this interval depends only on alpha and beta, which are given. So you see that I can always like change my sigma such that I'm not in that interval. Okay. So you see that, so those allocations may or may not be replicated by a model with a feedback rule. Okay. So if, I mean, the conditions are not very important, but if it happens that sigma is bigger than this guy, then my phi e will not be in this interval. I will have determinacy, so I can replicate the same allocations. But if it happens that my sigma is, is there, I mean, you can compute that, but it has no particular interest, then there are no determinate feedback models that can reproduce the stateful allocations. So there's no equivalence. So you see that, so if the truth is a sigma satisfying this condition, then those allocations cannot be replicated by feedback rule. So by assuming a feedback rule, I'm constraining the set of allocations that I can replicate. And maybe, the reality is within the set of allocations I can replicate, and then it's fine. But if reality is outside, then I'm in trouble. And then what will happen is that when I will estimate, given that I'm not allowed to choose this phi e, what I will have to do, when estimating, well, I will basically have to bias some other coefficients to make sure that I enter in that box, that I have determinacy. So I'm going to create a bias. Okay, so that's the so that's the key problem with this determinacy bias. It's this absence of like a back and forth equivalence between the two worlds. Okay, so what I can do in this simple world, I can show you the bias actually. Under some, you see, I mean, it's a thought experiment, which is like a bit ridiculous, but it's helpful. So let me try to derive the bias that I have. Let us show that we can have some bias in estimating in this model, and yeah, so that bias, and you will see, I mean, people who are like much more econometrician than I am, may think, oh, that's just like misspecification bias, broadly speaking. Perhaps yes, but you'll see why we think that we want to use a different word for that. We call it like determination bias, but I mean, yeah, I mean, it may be that you don't like it, and then if you're kind of like a bit hardcore econometrician, I mean, I guess that it's just some misspecification bias. But the misspecification is that I wrongly, well, I mean, we'll see. Okay, let me do this. So let me do this this experiment. So let me try to estimate alpha in this world, and I'm going to make like some stark assumptions. I will assume that the econometrician can only observe y. Okay, so the econometrician doesn't observe the instrument I, and the econometrician, she doesn't observe the shock st, but only y. And let me assume that the econometrician knows all the parameters of the model but alpha. Okay, so where it's so it means that if the world is feedback, then the econometrician knows the value of the feedback parameter. Okay, but if the world is a state rule, but the econometrician thinks it's feedback, he knows the value of this equivalent phi. Okay, so this is the part which is a bit weird. I mean, weird. It's a bit like yeah, it doesn't make much sense in in reality, because why would you know this? Because to compute this, you need to know everything. But that's that's just the assumption I'm making here. And so I know all the parameters. So the only thing I want to estimate is this alpha. Okay. So I have like one parameter to estimate. I have like one variable. So you can think of maximum likelihood as being just like GMM or moment matching. So I will simply need to match the variance of y. Okay, and I will need to find. I will solve the model as a function of my alpha hat, and I will have the variance of y in the model as a function of alpha hat, and a lot of other things that I know. I will have the observed variance of y. I will solve this equation and I will find the an estimate for alpha. Okay, so I'll show you exactly how it works. And you can think of it, it's maximum likelihood. And let me assume that the true alpha is 0.9. For my graph, it's kind of like it's easier. Okay, so how do I do that? So I will do two things. First, assume that the world is a world with a feedback rule, a Taylor rule, but I'm using as an equation, I believe it's a state rule. Okay, and then I will do the converse. So exactly as I did before to look at the equivalence, but now for estimation. Okay, so let me assume that the DGP, as I said, is a feedback rule. So this is what yeah. Okay, so let's assume that in reality, central banks are following Taylor rules. So econometricians who are estimating the SG with the Taylor rule, they're right. So, but now for some reason the econometrician has I've been convincing enough so that the econometrician now is estimating the model with the state rule. Does it hurt? So what is the econometrician doing? So I'm the econometrician. So I believe that the world is the state rule model. So if the world, I'm sorry, I'm going back. If the world is state rule model, I know that this is the solution, right? So from there, I can compute the variance of y. That will be this guy at the square times the unconditional variance of S, which is 1 over 1 minus rho square. Okay. So under my belief that the model is a state rule model, I know that this is the variance of y. Okay. And here I know all the parameters but my alpha hat. Okay. So this is what I believe. And so what do I estimation is solving that this is equal to what I see in the data, dy. Okay, so I'm going to solve this and I will find a solution for my alpha hat. So note that here, it's because it's a variance, there's a square, so I will have typically two solutions for alpha hat. So I'll tell you how what I do with those two solutions. So now, being like the one of the course of the paper, I know that if the DGP is a feedback rule, I know that the variance of y is equal to is obtained from that formula. Okay, because the model is the feedback rule. So you see that this notation is the variance of y when I believe that the model is a state rule, as a state rule, and that's the variance of y when the model has a feedback rule. Okay, so this is the truth. So that is the true value of the variance of y. So now estimation is solving that this blue term is equal to this blue term, solving in alpha hat. Okay, so we'll find that alpha hat is a function of all those parameters, including alpha. So if I find that alpha hat is alpha by solving this, it's unbiased. If I find that alpha hat is not equal to alpha, then I have a bias. Okay, so what I will do is that I will kind of like draw this function here, and show you what estimation is doing. Okay, so here's what I do. So this is the variance of y, and that's what I observe in the data. Okay, that's the variance of y that I observe in the data, is the dashed line. So knowing the DGP, I know that the variance of y, when the model has a feedback rule, that's the DGP, and as a function of alpha, it's this function here, that goes up here, it's plus infinity somewhere, and then it goes down here. It's this function. It is this function that is here, right? So you see that for alpha equal 1 over rho, it's infinite. Okay, so now I know that the variance of y is generated somewhere on that lines, and I know that the value of alpha is 0.9, so that's why I observe. Okay, of course, it's equal to this because the variance of y has been generated by this model. Okay, so now I'm the econometrician. So I believe that the world in the real world, the central bank is following a state rule. So as a function of alpha hat, that is the formula that is giving me the variance of y. Okay. So what do I do when I do the estimation? I'm computing this line here, and I'm looking at the alpha hat for which it's equal to what I see in the data. It's moment matching, if you want. Okay. And you see that I have two values. I have one, which is the right one, and I have one which is wrong, which is biased. So how do I do that? Well, I have an extra identifying assumption, which is determinacy. Okay. So then I can look in this on the alpha line at the values of alpha for which I have determinacy and the values for which I have indeterminacy. And the split is below 1 and above 1. Okay. So oh, well no, it's 1 over rho here. Sorry. So I know that, and you can prove that one of the two values is always in the indeterminacy zone. So I'm not going to estimate that one. I'm going to reject that one. And so the only my estimated alpha hat is equal to alpha. Okay. So for people who, for example, use dinar, this is what dinar is doing behind the scene. So dinar is, think of dinar as just like randomly drawing an alpha and checking if Vy is equal to if the variance of y is equal to what we see in the data. But before doing that, dinar is checking Blanchard-Kahn conditions. And if Blanchard-Kahn conditions are not satisfied, that parameter value is discarded. So if you draw that one, that doesn't satisfy Blanchard-Kahn condition, so it's discarded. So this is what I say when I say one of the identifying assumption is that is determinacy. Okay. So you see that here. So what do I have? I have the fact that, okay, assuming wrongly that the policymaker is following a state rule, whereas it's a feedback rule, it doesn't hurt. Okay, you precisely estimate without bias the value of my D parameter. Here it's just alpha. Okay, so now let me do the converse. So here I assume that the DGP is a feedback rule and the equalization believes it's a state rule. Now let me do the opposite. Let me assume that what the econometricians we know do, that they assume that there's a Taylor rule, but let's assume that in reality that's a state rule. Okay, let's see what happens in that case. So again, now I'm assuming that the DGP is a state rule, but the econometrician believes it's a feedback rule. Okay, with coefficient, the equivalence. So the econometrician will do the same. So now, I'm the econometrician. I solve the model. I believe the model has a feedback rule. So this is the value of the variance of y as a function of my alpha hat, which I'm trying to pin down, and I know all the other parameters. Okay. I compare this to the data and I solve to find the right alpha hat. I mean the alpha hat. Okay. Me being the like the co-author of the paper, I know that the DGP is a state rule, so I know that this is the true value of the variance of y. Okay, so I'm going to again solve for this blue term equal to this blue term, and I will look whether the alpha hat is equal to alpha or not. But you see here the problem is that it could be that this phi e is not in the determinacy zone, and if it is the case, then I'll be in trouble, and I will have to bias my estimate. Let me so I'm showing you the case that doesn't work. Okay, so if it happens that what the policymaker is doing is such that the equivalent feedback rule gives determinacy, then it's fine. But I'm looking at the other case. Why? Well, because that's the case which is kind of like new, and it's also what we will find in the data. Using US data, we'll find that we are exactly in that case. So what is that case? That case is the following one. Okay, so the DGP is a state rule. So that is the value of the variance of y as a function of alpha according to the DGP. That's what I see in the data. Why do I see that in the data? Because when alpha is 0.9, that's the model is producing that value. Okay, so now let me again be the econometrician. So let me draw what I believe is the model. So let me draw the variance of y as a function of my alpha hat, but believing that I am in a feedback model. Okay, meaning that I'm using the formula for the variance that is the one when the model has a feedback rule. So it's there. So you see that again, because it's a quadratic equation. I have like two possible solutions. How do I select between the two? I'm looking at where is it that I am determinate. But here, for the true value of alpha, I told you that we are in the case where phi e, the equivalent feedback rule, is not producing determinacy. So when I look at where is the indeterminate zone, it's like that. So the true value of alpha is in the indeterminate zone. So so if I am dinar, I'm going to discard that value, and I'm going to end up with this value of the estimated value of alpha. So you see that instead of estimating alpha at 0.9, I would estimate it at minus 0.8 or whatever. So I'm completely biasing my estimation. Okay. So where is it that it's not the standard misspecification? If you think of the likelihood of the model, you see that I'm pinning down perfectly the variance of output. So the likelihood of the model is exactly the same as if I were not biasing my estimate. That because here you see that it's in both cases I make the instrument. I make a mapping from a linear space of dimension 1 to the instrument. Okay? And it's the same linear space. So I'm not I'm not creating any misspecification because I would not, consider all the possible variables to which the central bank is reacting. It's really that determinacy requirement that is creating this kind of like massive indeterminacy. So the idea is that, to put it differently, I need determinacy. The feedback parameter is such that I don't have determinacy with the true value of alpha. So what do I need to do? I need to kind of like twist the value of alpha such that I recover determinacy and I match the data. And this is there. It's possible to do that, but it's totally wrong. Okay. Good. So now let me, okay. So this is what I said here. Alpha is just identified, so the fit of the model is the same. But the problem is that we're biasing so as I said, it's not standard misspecification, I believe. I'll tell you later what's misspecification in this simple world, but it's obvious. So we call that, for the lack of a better name, determinacy bias. Okay, so let me perhaps, but this is a bit specific. So now let me assume that I'm going to do some simulations. Let me assume now that the economic solution observes all the variables and is estimating everything, okay, using maximum likelihood, okay. And so I'm going to do some Monte Carlo. So I will assume that the DGP is the stateful model, okay, and I will estimate, everything, like 1 million times, in two configurations. In the configuration in which there's no problem, and in the configuration in which there's a problem. So you see that the difference between those two configurations is the particular value of my state policy parameter, okay, which is given. That's part of the DGP. So it could be, that in real life I'm in the case where there's no problem, but I'll show you later that in real life we're in the case where there's a problem. Actually, that's how we uncover the problem. It's really going backward. Okay, so let me do that. So here, let me assume that I am in the case, you don't remember the condition, but it's the condition under which it's not a problem to think that the policymaker is following a feedback rule, whereas in reality, it's a stateful. So in that case, let me assume that alpha is 0.99, beta is 0.2, rho is 0.9, sigma is that value, and you can compute what is the equivalent phi in this world that would give the same allocation, and they are determinate. It's this value. So now what do I do? I estimate, I simulate, 100,000 times this model with finite length sample, and then let me report, like I do maximum likelihood every time. Let me report the estimates. So you see that I'm kind of like nailing the value of alpha, not perfectly because it's finite sample. But so you see that all the parameters are well estimated. Okay, so this is telling me, there are cases where assuming a Taylor rule, it's not a problem if indeed that Taylor rule can replicate the allocations of the true GDP. But now let me be in the situation where I'm changing this value of sigma, and now the value of sigma is such that, for this value of sigma, there is an equivalent phi, but that equivalent phi is in the interval, in the forbidden interval for determinacy. Okay, so that's the case where it doesn't work. So that's the case. I'm sorry to go back. I'm exactly in that case. Okay, I'm the case where the true value of alpha is in the wrong zone. But now I observe everything. And so what does happen? You see that now it happens that I estimate pretty well beta rho, but alpha, you see that is totally biased. I mean totally. Right? It's biased in a way which is like serious, meaning that not only the value is wrong, but the sign is wrong. Okay, so the sign is wrong means that if I look at the estimated impulse response of my estimated model as compared to the DGP, they will be like completely off. So you see that when things are going well, so here I show the black line is the response of Y to a S shock in the DGP with the state rule, and the other line, the thick light gray line, is what I estimate in the case there's no problem. Okay, in the case there's a mapping between the two, so it's fine. But that's the other one. So if I look at this impulse response, when I assume Taylor rule, if you want, but that Taylor rule cannot replicate the DGP allocations when alpha is at the right value, then I need to kind of twist alpha, and I get something which is badly wrong. Okay, so and I'll show that this is basically what is going on in the real data. Okay, so that's for my what is going on with this determinacy bias. Perhaps I can pause at this stage to see if there are any questions. I mean, here it's a bit it's a bit abstract, so why would that be interesting? I mean, it's interesting because it's what is going on in the data, in US data. Any questions at this stage or some clarification?
Frank, very quick
Yeah.
clarification. Yes. If the econometrician have information on I, is this the whole analysis still go through?
Yes. So here, I mean, in this Monte Carlo approach, the econometrician observes everything: S, Y, and I. So right. So it's not, but then I can easily show you like formulas, analytical formulas. So I'm doing like Monte Carlo, but here everything is observed.
Another question is, can you do reverse engineering, and given the model that you have, try to identify which empirical relationships, for instance, which correlations or which autocorrelations, whatever that can be observed to the econometrician that indicates that maybe we can fall in one world versus the other? You know what I mean?
Yeah. Here, no, that's the point. It's really, there's no way you can identify it. No, you cannot, because you have discarded. Okay, the answer is no. Here again, the likelihood, if you, yeah, I mean, like you don't lose anything in terms of likelihood by biasing. So no, there's no way you can. There's no way you can see it. There's no way you can see it.
What I meant is a logic as following. Suppose that the true rule is a sigma of this level, and that implies that if we assume the wrong rule, then we'll fall into the indeterminacy problem. Now that sigma implies a relationship between Y and I in equilibrium, which may be different than if we fall for another sigma. So that may indicate.
But that's the thing. It's not. It's implying exactly the same relation. So you see. So for example, so the relation between Y and S, I and Y, I and phi, it's exactly the same if you correctly get this phi E. and you do. But the only way to be able to do that and having determinacy is by biasing here. So there's no way you can see it. There's no way you can see it. The thing which is interesting is that so if you take this state rule wrongly, then it doesn't matter. You will that's not going to cause any bias. So the idea is that in one case there is bias, but you can't see it unless you can see it. And in the only way you can see it is that I'll do that later. I mean, if you estimate the same model with the two rules. So yeah, something which is important I should have said is that perhaps I said it. The state rule is encompassing the feedback rule. Remember, because any allocation with the feedback rule can be replicated. So if you estimate the same model with the two rules and you don't find the same thing, that's because you have wrongly imposed the feedback rule. So that's the only way you can see it. You're not even losing likelihood by being wrong in that case. And that's a very specific case. And what is specific is that, again, in both cases, the rules are mapping the same linear space into the instrument. So there's no misspecification in that sense. It's really, it's coming from the determinacy requirement.
Frank,
yes?
Sorry.
Yes. Yeah, sure.
I might be a bit confused because I mean, you never actually observe the data generating process. So basically, if the actual data generating process has multiple equilibria or indeterminacy, it's like this is kind of like a sad result in the sense of like, given that we don't know if the actual data generating process has indeterminacy. I mean, it's basically what are we? I mean, what do we do essentially? Like, if you want to do something with these Taylor rules or with these models, do we have to write a multiple equilibrium model or something like that? I mean,
okay,
kind of like I might be saying things that are totally out of place, but I mean, please correct me.
Absolutely not. And that's exactly why we are following that rule in the profession. We assume away indeterminacy. So it's like it's an identifying assumption. Maybe we're wrong doing so, but that's what we do. We say no, the world is not indeterminate. Some people, Schonfeide and Lubick, I mean, they have, or the other way, Lubick and Schonfeide, for example, have shown, how can you estimate allowing for indeterminacy? I mean, I can discuss this later on because that's, can still, what we do still apply, but it's a bit more involved. But here the idea is that that's part of the thing that we do. We assume away indeterminacy. If we're, as always, when you have like some identifying restrictions, if they're wrong, then you're toasted because there's no way you can test your identifying restrictions. So just so that's yeah. So that, I mean, it's really it's a very important question, and you're absolutely right to ask the question. And I guess like the profession has decided to answer the question by imposing determinacy.
I see. Okay.
Not everyone. Then if you, I mean, I'm happy to talk about what happens when we relax determinacy. The thing is that we still need some identifying restriction that will typically be some correlation between the sunspot and the fundamental shock, and that's enough again to create biases if it's wrongly assumed. But the plain and simple answer is that's we don't even consider the world with indeterminacy, and the more kind of like the more let's say the less smart answer is I mean by design when I press the dinar button it's removing if Blanchard conditions are not satisfied that that cannot be the solution of the estimation to the estimation.
Okay, I see. Okay, it's an uncomfortable conclusion. I mean, I guess that's what it is. Thank you.
Okay, so that's for my okay. So now the misspecification bias. Let me say that in one slide because it's obvious. So let me make the model like super simple. I'm not going to do the algebra because it's super obvious. So let me assume that this is the true model. So the true model is that I have output that depends on two shocks, right? and my instrument. Okay. And now, what would be a state rule in this world is that, the state rule will map this, like now this dimension 2 linear space with the two shocks into the instrument. Of course, if I assume that the feedback rule is mapping, a linear space of dimension 1, which is, y into the instrument, well, here I'm restricting to respond, with a with a proportion sigma 1 to sigma 2 to the two shocks, whereas with a proportion 1 gamma to the two shocks, whereas could be that in reality I'm reacting differently to the two shocks. So of course, if the truth is this and I assume this, well, that's misspecified. I forgot to include like the price of oil in the reaction function of the central bank, and then of course, and then I'm toasted. I'm going to get something which is biased. So it's a bit obvious, but we will see that. So you can compute the bias, but it's obvious. But that may be important, and I'll show that in big models and in small water. That's a big concern. I'll show you exactly how it works. Okay. So now I have like those two. I've set the scene. I have like those two, and I can quickly like show you. Do we find evidence of those two problems in the data? And here I can go, faster. So I guess I have like something like 5 minutes. Yeah. So that's enough. Or maybe maybe I'll take 6. Okay. So let me take. So I'm taking again that. My two equation model now I have parameters instead of numbers. Okay. So here you see that I have like written discounted Euler equation to be a bit more general. It's going to help for what we do, but you can think of this alpha y as being arbitrarily close to 1 as you want. So it's not really an issue, but it's going to be like a bit simpler to present what we do. Okay. So that's my model, and that's my policy rule. That's a Taylor rule. Okay. And you see that here the Taylor rule is not misspecified in the sense that it's reacting to a linear space of dimension 2 when there are like the state of the economy is of dimension 2. Okay, so it's fine. There's no misspecification in that sense. Okay, so we are exactly in the case, but we know that when we assume this rule, there are some conditions on phi y and phi pi. Remember, that's the Taylor principle, right? So it could be that it's hurting us, and it's going to hurt us actually. So what I will do a change of variable because you'll see things will be nicer. So let me replace IT minus ET of 50% by the real interest rate. I'm going to think in terms of real interest rate. So let me rewrite this rule in terms of real interest rate. To do that, I need to subtract expected inflation on both sides, but it's just it's just like a notation. Huh? So that's my Taylor rule. Okay, but it's exactly the same Taylor rule. It's just like I kind of like it's easier to think of that the instrument is the real interest rate, but it doesn't change anything. It's just like so that's my Taylor rule. It's a feedback rule. And now let me contrast that rule with another rule that will be a state rule, where I will make the real interest rate a function of the state of the economy. Okay, so you see that I am exactly in the case of my abstract example. Okay, so if I have some troubles here, it's really because of the determinacy bias. And so you see also so what is nice with this model is that you see that when I think of the rule in terms of a real rate rule, you see that this term here becomes only a function of the state. Okay, so I can solve that equation forward regardless of the second one. It's the system becomes triangular. And to have a solution, I need this alpha y to be strictly smaller than 1. Okay, but it can be 0.99999. It doesn't matter. Okay, it can be exactly 1, but I don't think that. I mean, we know that when we estimate those guys, this guy is never 1, so it's more than 1. Okay, so that's what I do. So I'm going to estimate a model with those two equations plus either that rule or that one. Okay, so note that given that this alpha y is smaller than 1, the equilibrium is always determinate under the state rule. Okay, so I'm exactly again in the case of my abstract example. Also think that you really need to think of a policy rule as, so you have like those two equations that are describing what the private sector is doing. And it's a kind of hypersurface. And what multiplicity is doing is choosing one point on the hypersurface, right? But the way it's implemented here, we don't care. So if I could specify multiplicity as choosing the output gap directly. Okay. So if I were estimating that model with that multiplicity rule instead of the real interest rate one, I will find exactly the same parameters. So this is where I say no. I don't. Here I'm not taking a stand on the implementation of the policy. Policy is just how to pick up a point on an hypersurface. Okay, so I will estimate that. It's a bit ridiculous to estimate such a simple model on data, but let's play that game. So, and then here we can do any subsample you want. It doesn't change anything, but let me use like the largest possible subsample and making sure that I replace the nominal interest rate by the shadow rate after during the ZLB. But you can stop in 2008 and start after post-Volcker. I mean, that doesn't change anything. And then let me calibrate the beta, the alpha, the elasticity with respect to the interest rate. Let me put no Euler discounting, and let me do some Bayesian estimation. So basically what I'm estimating is the slope of the Phillips curve, the shock processes, and the monetary policy parameters, which is what we do most of the time because all those guys are not well identified in the other case. Okay, so I do that, and let me show you like the estimation of kappa. So again, I'm using like it's the same model, quote unquote, but it's not because the policy rule is different. It's specified in a different way, but this rule is encompassing the Taylor rule. So if the truth is a Taylor rule, I will find the same estimates with that state rule. Okay. Good. So let me look at the estimation of the slope of the Phillips curve, and you see that with the state rule, the slope of the Phillips curve is 100 times smaller than with the Taylor rule. So we're exactly in the case, this kappa is like the alpha parameter before. Okay, and it seems that imposing a Taylor rule is dramatically biasing the estimation of the slope of the Phillips curve, meaning that a model in which the level of price stickiness was reasonable becomes a model which it's ISLM basically. Prices are like completely sticky. So which I guess is casting a doubt on on like doesn't make the model very reasonable. Okay, so there's indeed there's a big bias. So where's this bias coming from? It's clear if we look at how the estimated Taylor rule when we impose a Taylor rule is like it's what typically people find is that it's the rule. It's pretty harsh on inflation. It doesn't care much about the output gap. That's the Taylor rule. If I estimate the state rule, I could ask, okay, is that reasonable? It is. It's basically that estimation is telling me, oh, what the Fed is doing when there is a positive demand shock, the Fed does something that increases the real interest rate. Okay, when there is a negative supply shock, the Fed is like pushing down the real interest rate. Okay, so that's the same narrative as this one. But now what I can do, I can look at what would be the equivalent Taylor rule. What is the Taylor rule that would produce exactly the same allocations? And that Taylor rule is that one. And you see, it's a Taylor rule that doesn't satisfy the Taylor principle. Okay, so it means that we're exactly in the case where the equivalent, so if data are generated by this, and this is general, so data has to be generated by this. The implementation, I don't know, but in terms of state rule, this is what is going on. If you want to implement that allocation with a Taylor rule, you cannot replicate the same allocations, keeping the other parameters the same, because you have indeterminacy. So you have to basically twist the other parameters. And here, the parameter that you're going to twist is the kappa, is the slope of the Phillips curve. So we already, so in practice, we are confronted to this problem looking at the data. Okay. Okay. So I'm almost done. So let me perhaps skip that part where I do some extension. Let me skip so we also do like, small models, but a bit more, flexible, a bit more reasonable. Like, like the three-equation model, but you had habit persistence, you had a hybrid Phillips curve, and you estimate, and you find the same thing again, determinacy bias. And the estimate of the Phillips curve is like, goes to 0, basically. The estimate of the slope of the Phillips curve goes to 0. Or we can do some kind of like simple hang. That's this paper of Tobias Brewer and co-authors in the Ristad last year or 2 years ago. And again, with a Phillips curve, a wage and a price Phillips curve, and we find again the same thing, determinacy bias. And those are like relatively small models. So to give you an idea, let me just look at the habit persistent and Phillips curve, hybrid Phillips curve model. So that's the Taylor rule. And now if you want to write a state rule, of course, now the state is getting bigger, right? Because now the state is the two shocks, but also past inflation, because you have this hybrid Phillips curve, and also past consumption, because you have like the habit persistence. Okay. So you could think, oh, but maybe the central bank doesn't observe all those guys. But that's okay. If it doesn't observe those guys in practice, then those estimates will be 0, because that's it's more general. Okay. So now let me conclude by looking at so let me skip that one. The Spitz-Wouter model, which is kind of like monster model, 7 shocks, 36 estimated coefficients, 19 set variables. Okay. So this is what Spitz-Wouter are assuming for the Taylor. So again, you see that that's very different from the Taylor rule of the small model. So if it was supposed to match the narrative of central banking decisions, it should be the same, in all models. It's not. Okay. So now the state rule looks a bit more crazy, right? Because it's a mapping from a 19-dimension linear space to the policy rule. Okay. So you need to observe, like all the shocks, but you need to observe what would have been output the next period had prices been flexible. You need to observe what would have been the capital stock yesterday if prices were flexible, this kind of thing. That may look crazy, but it's, if it's crazy, if the central bank doesn't observe that, then those coefficients will be 0. Okay, so there's no, it doesn't hurt. Okay, so let me do the estimation. Problem is that the model is like a monster, so I can show you the estimates of all the parameters, but I'm not sure what to do with it. So let me show you one thing. So that's the Taylor rule estimated when you impose the Taylor rule. So this is Spitz-Wouter. If I do my state rule and I uncover what is the equivalent Taylor rule, I mean, it's kind of the same, right? So this is kind of telling me, oh yeah, it's unlikely that there is determinacy bias here. And we know that this model is like very backward looking. There's no problem of determinacy. But if you look at all the parameters, they're all different. But it's hard to know. So let me show you. Let me just flash impulse responses of output, inflation, and nominal interest rate to the 7 shocks. And I just want you to see that they are different. And then I do something which is more interesting. But so those are like the impulse responses. So the black line is with the state rule, and the light gray line is with the Taylor rule. So you see that it's very different. So I could come up with a story for each of them, but it's complicated, right? But it's very different. So and I'm going to conclude with this. Let me do something which I guess is what policymakers are interested in central banks is how do we explain inflation in this world? In the world, in the US. So let me do the variance decomposition of inflation according to the Spitz-Wouter model estimated with the Taylor rule. And I have like a very boring view of inflation, which is basically inflation is explained by nothing but the price markup shock is explained by nothing but the inflation shocks, which are those two shocks, which explain 88% of the total variance. And we know that those shocks is very hard to have like a structural interpretation of them. So now what I can do is that we estimate the model with my full rate rule that encompasses that one. So if the true rule is the Taylor rule of Spitz-Wouter, I'm going to find exactly the same thing. So if I do that, that's what I get. So it's a dramatically different views of what is moving inflation in the US. Now you see that it's basically 1/6 on all the shocks and nothing on the risk premium. but it's very different. So you get a completely different perspective on what moves inflation, and then if I were then to think, for example, what would be the optimal monetary policy given these estimates of the D parameters, I would get like a completely different answer. So okay, conclusion, and I'm done. So the specification of the monetary policy rule matters big time, and I don't think that we have any good reasons to use some incarnation of the Taylor rule that we're using. There's evidence, in the data of both determinacy and misspecification biases, and here they are really like the small models where it's really a determinacy bias, because in the small models, basically often the Taylor rule is not misspecified in terms of responding to the state. And then in bigger models, there's a really big misspecification. So the conclusion is that, I think that what one should do is that, when someone is estimating, a DSG model with some sort of Taylor rule, one should also like re-estimate the model with a state rule that is encompassing that sort of Taylor rule, and check if the results are different or not. And if the results are different, and typically they are for the Spitz-Daughter model, then then there are like serious biases in using the Taylor rule. That's it for today. Thank you very much. I'm happy to. I'm sorry I took a bit more time, but yeah, I'm happy to kind of like take questions, comments, people screaming, everything is fine. Okay, cool. Thanks.
Thank you so much, Frank. So, is there any question or reaction?
I have one. So, in the sense of how to basically know a bit more about the underlying data generating process, I mean, couldn't you use some sort of like reduced form evidence, like a VAR evidence or structural VAR evidence about how, for example, the monetary policy rate reacts to another type of shock, like a TFP shock or something like that, that you, have a good sense that you're identifying it. So basically, like that the shape of the Taylor rule or the overall responses of the model align with that structural VAR evidence, a bit like what Cristiano, Eichenbaum, and Evans do at some point.
Yeah, this you can do, but that will be testing the whole specification of the full DSG model, not particularly the last equation. In a way, having a state rule is being totally agnostic, is letting the data speak as far as monetary policy is concerned. Okay, so basically by doing this, you would test basically all the other restrictions coming from all the other equations, which is fine, but that has like in a way, there's no reason why one should not use the state rule, because it's just not putting any structure on something for which we don't have any micro foundations to put structure.
Okay, makes sense. Yeah, thank you.
Hi, do you hear me?
Sure.
Yeah, hi. Benjamin from the bank. Really cool paper and really worrying for us who do this kind of stuff. But I just a question about the last example where you compare the Smith and Bowter's two versions. How do you deal with the priors for your real rate model, in the sense that they are equivalent to the priors that are set for the Taylor rule parameter in the normal Smith and Bowter? Because there it could be that is the bias that you discussed, or it's just that the priors on the feedback rule are too tight or tight in a wrong way of the space. So is there a way for like do a system priors and endogenous prior kind of strategy so that the priors on the real rate, the state rule, are equivalent to the priors of the feedback rule?
Yeah, no, it's a good question. Yeah, so it's complicated because having kind of equivalent priors would amount to kind of like for each possible set of parameters drawn in the distribution of the in the priors, you will need to check whether you have determinacy or not to see whether you can map the other one. So that's in a way is that I don't know how to do that. So it's true that here if I had if I had like very tight priors here, it could be that, it's just that my priors are, I don't find the same thing because my priors are too tight, and the truth, and are tight in a way which is excluding that particular restrictions of those parameters, right? Because this rule is a restriction on those sigmas. So you're absolutely right. So then what we do, we have so I have to remember, we have as flat as possible priors. So I think perhaps they are completely flat for the sigmas, right? But it's true that then, it's complicated because then if you think of the joint priors of the policy parameters here with the other parameters, like the other deep parameters, then of course, there's no way they can be the same because, it would be complicated. I could, for each set of sigmas, I could kind of compute what are the equivalents rho, phi p, phi delta y, and then make sure that the joint distribution of my priors are the same in the two model, but that's just insane, to try to do that. So we just by having now, I'm sorry because I completely forgot. I think we have completely flat priors on those ones, so that we are not excluding any we are not excluding that this is the right representation.
Yeah.
To me, in an ideal world, if I could estimate this by maximum likelihood, I would prefer, right? Because I wouldn't have this problem. But yeah, so I think it's just So my answer is yes. That may be an issue, but flat priors.
But
So
you could compare.
then
An easier way is to do the opposite. I don't know if you do it, but have as flat as possible prior for the fees. So then you know that the difference, it does not came for a possible misspecified priors or that, and it's actually the bias that you're talking about. But thank you.
It's a very good point. So I forgot. But that if you haven't done that, we have to do that. We should do that. Absolutely, we should have flat priors on the parameter table. That's a very good point. Yeah. If we haven't done that, we'll do that. Thank you. It's a very good suggestion. Yeah.